Okay, fine. Hello, good evening, everyone. Whoever has joined this meeting. Um, I would request you to now start asking your questions because this is a interaction session. So, first session that you're having for this course. I hope you have watched the videos of this week. So this session is particularly to address your questions. I'm not going to be talking here. I'm only going to be answering your questions. So you have heard me enough. I've talked enough in the videos. So you should start asking your questions. So I see one question here. How will you teach to handle the real-time problems? So as we, so from what I understand, I see that the question is to I mean, this is a question to the feedback NPTEL team. I see a lag between what I say and what is appearing in the video. So is that expected? NPTEL team, can you answer my question on the chat window? So I'm not able to talk continuously. No. It's not about them posing the questions. I mean, whatever I'm saying, it's appearing in the YouTube video with a lag. No, there is something wrong because I'm not able to talk continuously. Okay, so I will have muted the YouTube. Okay, got it. Okay, fine. Sorry. Yeah. Now I get it. Okay. So again, welcome everyone. I was not supposed to do something. I think I got it right now. Okay. So let me take the first question. What is the manufacturing process of the? Okay. Before that, Ranjit had a question. How do you teach to handle real-time problems? So I think you have to be patient and listen to the course. We will be handling real-time problems during the course. There's a question from Suraj. What is the manufacturing process of an optical fiber cable? So, the manufacturing process is not very easy process. So, what is typically done is whatever is the refractive index profile you need to create, glass preform of the same refractive index profile is first fabricated through a chemical vapor deposition process. And so essentially, you will make a magnified version of the fiber that you want to make. And then these are drawn through the towers, this fiber drawing tower. So this preform is, pushed from the drawing tower, and you are allowing the glass to melt through a very fine hole, and you set your temperatures, pressures, and the pulling speed all right, and you will draw it to the right dimension. There are a couple of commercial fiber manufacturers in the country. I can probably share a link to the YouTube link to the manufacturing process. In fact, if you look at the webpage of Corning, which is one of the oldest companies that has been doing fiber optics, they have a video that shows how this process of fiber drawing is carried out. We wouldn't be doing that in the course, but then that's a very interesting topic. The next is, how is the width of the pulse important for fiber optic communication? So you saw, I think you have not seen the video on digital modulation because you see you're modulating your data in ones and zeros, and the duration of your one is actually decided, that's the width of the pulse. So if you want to send data at a rate, for instance, 10 gigabits per second, your duration is 1 divided by 10, which is 0.1 nanosecond, which is 100 picosecond. But if you want to send your data faster, obviously your on time of the pulse is going to be much shorter. For instance, if you want to send data at 40 gigabits per second, the on time is going to be much shorter than that, right? I mean, you will do 1 divided by 40 gigabits, it will turn out to be 25 gigs. So essentially, the width of the pulse is decided by how fast you want to send your information. What is the current scenario of free space optical communication? So I really don't understand the question. What do you mean by scenario? So, there are demonstrations of free space optical communication. There are demonstrations of high-speed free space optical communication. So I really didn't get the question. There are also commercial demonstrations of free space optical communication. Arjun has a question. Can you elaborate more on Nyquist filters, and why is Nyquist bandwidth need to be considered one-sided bandwidth? Okay, so that's an interesting question. When we talked about bandwidth, let me see if I can project the. Just give me a minute. I'll try to see if I can project something on the screen. I suppose you're able to see my screen now. Something projected on the screen. Yeah. So you see, if I have an optical carrier, which is here, I hope you can see my arrow, and I'm modulating with a speed of, let's say, 10 gigabits per second, I will see that if I do a typical non-return to zero modulation, I'll see that the way the spectrum fills is what I've shown here, right? It extends from minus B to plus B, which is on either side of the carrier frequency. Okay. Now, which means that I'm actually occupying 20 gigahertz of frequency spectrum when I'm trying to do a 10 gigabits per second non-return to zero modulation. If I try to send only up to the first null, it now means that so this is the most common way of modulation. This non-return to zero on-off key, right? But it turns out that when we are trying to look for sending more bits in a given spectrum, what we need to do is to find out mechanisms by which we need not use the entire 2D. The question is, can we use a lesser bandwidth to send the same information? Okay, and that is possible by Nyquist shaping. So according to the, so what Nyquist bandwidth says is, you need only a bandwidth of B, for instance, here, right? You need only B for, you need only a bandwidth of B. You can do mathematical process of shaping the signal such that the minimum you will need to send your data is actually B. If you can do some kind of shaping in the time domain or in the frequency domain, if you can do some signal processing, you can actually transmit this information, which is at 10 gigabits per second, with a bandwidth B on either side, the total bandwidth B on either side. Now, this one-sided bandwidth comes because when it is unmodulated, right? So when you're modulated on the carrier, it is actually always two-sided bandwidth. So I hope that answers the question. I have a question before Arjun's from Senthil, which says assignment questions are expected in problematic. I really did not understand what it means. I would expect, please explain your question, Senthil. There's a question from Anupam. What types of modulation is used in fiber optic communication? Does modulation is necessary to transfer signal through fiber? Yes, of course, modulation is necessary to transfer because you're trying to use light as a carrier. So you have to modulate light to transfer your information. What type of modulation is used? As I said in the lectures, conventionally we use non-return to zero on-off keying, which is on-off signaling. But the last few years, we have started using phase modulation. We also talked about QPSK and 4PAM and 16 QAM and so on. So those are the modulations that are currently used in optical communication systems. Monojit, is it possible to send electricity transmission through optical fiber cable? So this was answered to you on email also. No, it is not possible to send electricity through optical fiber cable. Although what we have is in electrical cables, current carrying cables, we have optical fiber embedded. So these are called as OPGW cables, fiber in OPGW cables, which are essentially the ground conductors in power transmission lines. We have started putting fiber in the power transmission line so that wherever power goes, you can reach the optical communication there, right? So it's the other way around. In electrical cable, we are putting optical fiber and sending communication. The physical optical fibers are embedded in the OPGW cables, and we can send information through that. Vasundhara, question is, what is the difference between PAM2 and PAM4? Please go back and go through the lectures once again. It is explained very clearly. PAM2 is 2 level, on and off. PAM4 is 4 levels. So you will have between, let's say, 0 to 4, you will have a level 0, a level 1, level 2, and level 3. So there are kind of 4 levels which you use to signal in PAM4. So number of bits per symbol in case of PAM4 is basically 2 bits per symbol. So let me again show that to you in the slides. So I hope you can see the screen now. So you see in PAM2, a level 0 represents 1 bit, level 1 represented another bit. So when you shift between 0 and 1, you have the low and a high and a high and a low and so on. So one time slot, which is marked here as one time slot, you have only 1 bit that will represent, 1 bit that is transmitted. Whereas in PAM4, you will see that during the same duration of time, because you can have 4 levels possible, you could transfer 0, 0, 0, 1, 1, 0, and 1, 1, which means that you can send 2 bits in 1 bit slot. That is what happens in PAM4. So I hope that answers your question. It's a question from Vishwanathan. Why do we see a fuse in a fiber? Can we reuse the fiber with a fuse? So, you know, fuse in a fiber happens when the entire fiber melts. So if it is a fiber fuse, this typically happens not in the fiber which is used in communication systems. These fiber fuse happens in those fiber laser systems which uses very, very high powers of the order of kilowatts of power. So what happens there is a part of the fiber burns, and due to some unexplained phenomena, it's some thermodynamical phenomena that happens, the burn actually spreads along the length of the fiber. And once the entire fiber is burnt, you can't reuse it. But this is different from the damage that you see when you have a fiber. For instance, sometimes what happens is the edge of the fiber or the tip of the fiber gets damaged. In that case, you can cut and reuse the fiber. But if the entire fiber is fused, you can't reuse the fiber. There's a question from Michael Jordan. If I want to transmit data at 100 Gbps, I can go with either 64 QAM or WDM system or 4-channel 25 Gbps OK. I like to know which one would be better with the 1330 transmitter system where there is no dispersion. So some of these things are coming up in the course. We do deal with some kind of these kind of questions, but to give you a heads up, if it's a 1310 nanometer system, this WDM is not a commonly used feature in 1310 nanometer system, right? WDM grids are typically designed in the C band, which is in the 1530 to 1560 nanometer. So if you were using 1310 nanometer, and if you can use something like coarse WDM, right? WDM, which are where the wavelengths are slightly widely separated, you could use 4 channels of 25 gigabits per second. Okay, that will be the simplest solution. Simply because typically the coherent transmitters and coherent receivers are typically available for 1550 nanometer. So I would recommend if you can take 4 channels of around 1300, 1320, 1310 and so on, and modulate 25 gigabits data on each of that should be the better solution. There's a question from Ranjit. What is the criteria to carry out perfect communication through optical fiber? So that's a very general question. There's nothing called perfect communication in an optical fiber. You always, the way the communication links are designed is ask yourself the question, what is the data rate to be supported? What are the link distances you want to handle? And design and what are the error rates that are acceptable. Then you design, you pick a transmitter, you pick a receiver, and you choose the wavelengths such that these conditions are met. There's nothing called universally perfect design. A design that was perfect today, tomorrow, if you increase the data rate from 100 gigabits per second to 1 terabits per second, it's not going to work, right? So this is like any other design. You first have to ask yourself these kind of questions before you can come up with the solution. So another question from Suraj. What about core cladding? So the question is not clear. So Suraj, can you expand your question? So this is a request to all those who are participating. Please formulate your questions in full sentences. And I don't. If you write part of the sentences, I won't be able to make out what you are asking about. Okay. So please try to formulate your questions as full sentences. So I'll wait for Suraj's full sentence. Michael's question is again, you mentioned NRZ is used in the current system, which requires clock signal as well. Why can't we use RZ, though the bandwidth required is double that of NRZ? So this is again, initially there was a lot of discussion or in the industry about whether to use RZ or NRZ. It turns out that, even though the clocks are very, very easily discernible in RZ, people prefer NRZ because clock recovery is actually not a complicated task. And as you pointed out rightly, the bandwidth required for NRZ is only half. So you would like to send more spectrum, more data in the same bandwidth, which is why RZ is preferred. The other reason why this is why NRZ is preferred. The other reason why NRZ is preferred is because if you take the return to zero signaling, in every bit slot, the pulse is coming back to zero, which means there are a lot of transitions from 0 to 1 and 1 to 0 happening. Later on, when we look at non-linearity in an optical fiber, you will realize that this transitions from 0 to 1 and 1 to 0, this dp by dt, that is what actually causes a lot of nonlinear phase distortions. So even though your power is small, the nonlinear phase that gets added becomes something that you cannot ignore in case of RZ signaling. There's a question from Senthil. What is the benefit to select 1550 nanometer in optical based communication systems? So that is again a topic of discussions that will come in the coming weeks. There are two criteria which helps us to decide what wavelength to choose. I never said that 1550 nanometer is a universally deployable wavelength. I mean, again, as I said, it depends on what kind of link you want to establish. Okay. Suppose, there are two major criteria here, which you will learn in the next few weeks. First criteria is attenuation in the fiber. Second criteria is dispersion in the fiber, right? If you want to go for very long lengths, you want your attenuation to be small because you want the loss to be small, and you want your dispersion to be minimal so that the pulse doesn't spread out. Now, for those who do not understand what is dispersion and attenuation, you have to please wait. It is coming up in the next weeks. Now, it turns out that 1550 has minimum attenuation, whereas 1300 has minimum dispersion. So, if I want to, for instance, set up a link, let's say a campus network or a network which is a short distance, a network in the data center, for instance, right? The distances are like 100 meters or 200 meters or less than a kilometer or even 5 kilometers, right? It doesn't make sense to me to actually, use 1550 because it's a short distance. So, I mean, even if there is loss at 1300, I mean, I can, the loss is not, the distance is not much, so the net loss is not much, whereas the dispersion is 0 for 1300, right? So I don't have to do any kind of dispersion compensation, especially when I go for very high data rate systems. So that way I would prefer 1300 nanometer for such short distance link. But having said that, if I go for very long distance links, I need to know, basically have amplifier in the path because the length of the fiber is large, so I need to keep amplifying it. And there are no 1300 amplifiers that are available today. The technology for amplification in 1300 nanometer is not available today. So for long distance, because the loss is low, I would use 1550 nanometer and I deal with dispersion compensation. So all that we will talk in detail during the course. Let me see what's the next question. There's a question from Vishwanathan Shankar. What role is optical communication playing in the development of smart power grids? This is again a very general question, so I will answer this to the best of my understanding. So in case of, as I told you earlier, the recent trend is to actually deploy optical fiber actually when you make the power cables, the general trend today is to actually use optical fiber embedded inside the power cables. So there will be about 16 to 64 fiber cables within a power cable. The idea is that you can communicate through these power cables by accessing these optical fiber cables. So in that sense, optical fibers are currently used even in smart power grids. And if you were to actually do some amount of communication in terms of what, I don't know, whatever is the requirement in a power grid, that can be used. It can be used for commercial communication also. What is also seen is that companies could use this, or deployers could use this for basically identifying if there is a fault in the power line. For instance, let's say there is an unusually large current flowing through one of these power cables. The temperature changes, and then one of these fibers can be used as a sensor to detect changes in temperatures, or it could be used to detect a sag in the power line, strain changes through the certain scattering processes that happen in the fiber, which we will talk about towards the fag end of the course. And then you can use the same fiber cable not just for communication, you can use it also for sensing what is going on in a distributed manner, right? So that sense also optical fibers can play a very significant role in the power smart power grid also. The next question is from Capiro Mistri. OFFT Optic. Off topic, sorry. Okay. Is it possible to done some simulation optical fiber? So if I understand your question is, can we demonstrate some simulations with optical fiber? We are doing that towards the later part of the course, especially in the digital signal processing. We are trying to do some simulations. We can also try and show you some additional simulation material. So what we do in our research lab is that we use either MATLAB or one of the simulation softwares to identify, for instance, the modes of a fiber given as refractive index profile, or we use MATLAB or some such simulation software to emulate the communication system. So some of these are coming up in the later weeks. This is will not be graded, but this will be additional material that will be available to you, which you can use to simulate some of the systems that you are working with. How many colors are used to identify optical fibers? So Monajit, this is a completely industry kind of standard. In an optical fiber cable, there are multiple colors to identify. Off the top of my head, I do not remember how many colors are used. I really don't know. So, but then I know that you jacket the fiber with different colors so as to identify. So this is you can look up on Wikipedia or something. There are some standards, standard colors people have used. Maybe 10, 12, I do not know. Why the OLT cannot be binded with third-party ONU? So Bhargava, can you please expand your question? I know you're talking about the passive optical network, but I didn't quite understand the question. So Bhargava, can you please expand your question? The next question is from Shivansh. Optical fiber, how work in terms of networking? So again, you have to be patient. This is only the first week of the course. We do talk about optical networking towards the later part of the course. So please be patient and stay with the course. We will do a significant amount of optical networking in the later part of the course. Arjun has a question again. Do we use NPTEL team, can I go on? Was there a connection issue? Okay, fine. Yeah. So I'm just going ahead. So I'm just repeating Arjun's question. Probably we lost the connection at some point there. Why do we use RZ modulation somewhere? So as I said, the specific advantage of RZ modulation is that every bit there is a high and a low. The bit goes from high to low, which means that identification of the bit slot, where your bit slot is, becomes easy, because you know for a fact that after every bit is over, the bit slot would have, or the power would have come to 0. So the clock recovery becomes very, very easy. It comes with very strong clock tones. But having said that, it requires twice the bandwidth, because you're going high and low. The bit transitions happen very frequently, so which means that you need a larger bandwidth. So commercially, they are not being deployed anywhere. There could be some specialty experimental deployments which are working with RZ, but commercially they are not deployed. I will just check with Mahesh once again to make sure that the session is going uninterrupted. Is everything going fine?
Yes, ma'am, everything's going well, ma'am.
Okay.
But that time is some internet issue, that's why it is lost.
Yeah, because I am not able to see the video on the YouTube live, so I thought I just...
It's coming close, ma'am, right now.
Okay, but at least in my screen it is not coming. Yes, got it. Got it. Okay, fine. Okay, so we were at Arjun's question. I hope that answers Arjun's question. Dev Datta has a question. Gain versus frequency peak shifted right due to temperature for lasers. Why is this thing happening? Dev Datta, I suppose you're talking about semiconductor lasers. I would suggest that please ask questions related to this week's content. Because lasers, all these questions will get answered after we go through the lectures of week 2, week 3 maybe. Lasers are coming up in week 3. So we will take up this question again in week 3. It's a question again from Bhargava. How does temperature play in speed and bandwidth? Actually, as far as fiber goes, the deployed fiber goes, in the normal range of operating temperatures that we have, so the fiber deployments are probably rated from, say, minus 20 degrees to plus 60 degrees temperature, plus 70 degree temperature, so on. We don't see a lot of difference in the speed, because the refractive index change in that temperature range is not significantly large to bring in any change in the optical communication system. So unless you're laying your fiber in some extreme weather conditions, even in extreme weather conditions, you can basically calibrate and then start, kind of using that. So I would say there's not much of a difference. Bhargava says GPON and EPON. So GPON and GPON, please be patient. Go through the lecture contents. It is coming up later during the course, and we can discuss in detail when we are dealing with the content of the course. Greatly appreciate. I plan to have this, interaction session every week on Friday at 5 p.m. So that you get to ask your questions regarding that week particularly. For topics which I'm not going to be covering in the course, I will try to answer. But the topics which are going to get covered in the course, I will request you to be patient, go through the course content, and then we will discuss. You will be asking your questions with a little better understanding. Arun Kumar has a question. What's the difference between single mode fiber and multi-mode fiber and applications? Arun Kumar, please wait. I think it's coming up in the 5th week or 6th week about single mode fibers and multimode fibers. So be patient, go through the course, stay with the course, come up to that point. These are being discussed during the videos. So if you're still not able to get it, I'll be happy to explain once again. There's a question from, I don't know whether it's a question or a comment from ANR. Color of cable, black and orange. Again, I'll repeat my request. Please type in your questions as a fully formed sentence so I understand what you're trying to ask. MAC is binded and third-party OLT doesn't accept through GPON, EPON, ONU. So as I said, Bhargava, please stay with the course and let's come to the point where we are talking about networking and we will discuss this. Passive optical networks will be a part of the course. Yes, passive optical networks are being considered in the course due to in the later part of the course. So the course is structured, I'll repeat once again, the course is structured as the week 1 was in general the idea of digital communication and bi-optical fiber communication. Then we will start talking a little bit more details about the transmitters we are using, the LEDs, the lasers, their functioning, what decides the bandwidth of LEDs, how do you choose the LEDs or lasers, and then we will talk about receivers, and then we'll talk about fiber, and then we'll talk about receiver, then we'll talk about a link, and then we'll talk about the components which will make up the link, and then we'll talk about link design, and after that we will talk about networks. So you have to stay with the course. Whether this video will be available after this live session, I have to, the NPTEL team will answer. I request the NPTEL team to answer that. Ritesh, frequency modulation difference and amplitude modulation. Yes. So frequency modulation is definitely different from amplitude modulation. For an electromagnetic wave, the two different amplitude and frequency are two completely different ideas. Amplitude is the strength of the wave, whereas frequency is how fast is the wave oscillating. You can do frequency modulation for a high and a low. You can do FSK. So I think in the lecture 3 or lecture 4, we talk about FSK, where you can change the frequency depending on the pulse. But typically that is not done in optical communication, because you will realize later in the next week that it's not easy to change the frequency of the laser so fast in the so predictive manner, right? So FSK is not done for optical communication. It's a question from Arun Kumar. At 1383, light energy has been absorbed. Is there anything to do with bond length, or what is the logic behind this, since other wavelengths it is not happening? So again, I am explaining this in the later part of the course. Around 1300, there is absorption in the, I'm really glad that I have a lot of enthusiastic students who are familiar with optical communication, but these are questions specific to the content that's going to get discussed. So I will say, please stay with the course and we will discuss this whenever we talk about attenuation in fiber. To give a quick answer, the fibers that are made these days do not have an absorption peak at 1380 or any of those wavelengths. Chowdhury TV, is it possible to electricity transmission? I've answered this already. No, it is not possible to have electricity transmission through optical fiber. Okay, the next question from Shanmugha Prakash is, during fiber communication, will evanescent field affect the signal? That's a very nice question. So it looks like you have some magnetics in background electromagnetics. So as you know, evanescent wave does not carry energy. So it does not affect the optical fiber propagation. Having said that, you can use evanescent waves to tap the signal out of fiber. Right? The common misconception is that you cannot tap from an optical fiber. That's what many textbooks also write, that optical fiber communication is good because tapping of information is not possible. But that's not true. You can actually tap out this information from the evanescent field, right? So in general, the evanescent wave for a jacketed fiber, the evanescent wave will not have any role to play. But if you're using, or you can also use evanescent wave for sensing, right? You can kind of remove the cladding from a part of the fiber, and then you can put a liquid there, and then the concentration of the liquid can be sensed by the strength of the evanescent wave and so on. So that's a different class of optical sensors. You can use them, but in regular communication systems, evanescent waves do not play any role in the communication system. Will you please elaborate about Fourier transform you told this week apart from modulation? So, as I said, the only requirement for this course was signals and systems. So, you have to go back and revise your idea of Fourier transform. This will keep coming in the course because we are going to be dealing with signaling that is happening in the time domain, and any signaling that is happening, any change in time domain, it has a repercussion, or it has a corresponding change happening in the frequency domain, right? So Fourier transform ideas should be, you should have some basics of Fourier transform. Unfortunately, that's not a part of this course, but to give you an idea, you can say that Fourier theorem basically connects the changes happening in the time domain to what is happening in the frequency domain. And it is important to have this intuitive feeling between the changes in the time domain and the corresponding Fourier spectrum to appreciate many things that is happening in a communication system. So I would request you to go back and review some of the NPTEL videos. You can send me an email in the course forum. I can refer you to a YouTube video which is explaining Fourier concept, and you can revise from there. It is very hard to explain like this in a conversation, right? So I can if you can send me an email through the course forum, I will direct you to a YouTube video, NPTEL video again, which explains Fourier theorem and this idea, so that you can reinforce this before you do this course. Ravi Patel, there's a question. If fiber optic cable has a higher bit rate, then why are we using microwave links connect to BTS BSC? So I don't understand what is BTS BSC. So Ravi, if you can explain what is BTS BSC, that would be great. But of course, you cannot compare fiber optic cable with a microwave link because these are completely two different channels, right? Microwave link is useful when you have free space. You can basically connect through air. Whereas to have a fiber optic cable, you need to have a physical cable laid between 2 points, right? So for example, I cannot use a cellular phone with a fiber optic communication, right? I mean, my cell phone, one is the channel is air and the channel is fiber, right? So I don't think we can compare between the two, but you're probably specifically asking something about BTS and BSC. So when please expand that, then I can answer specific to that. Bhargava's question, why is there no hardware available for direct fiber to internet without using it media converter such as LAN? Okay, this is very interesting. In fiber to the home also, you have the fiber coming in and then you have a media converter, simply because your computer is working with electrical domain. The computer has boards which work in the electrical domain, and you need somebody to translate the language spoken by the framing standards of fiber versus framing standards of Ethernet. Having said that, the framing standards of fiber is now getting to Ethernet standards, so there's not much of media conversion that is happening. But you will still need a device to convert from optical domain to electrical domain. So some of this, we are doing it in the optical networks part of the course, which comes in the last part of the course, where we are trying to see what kind of framing or what kind of process is this media conversion doing. Any type of OTDR is a part of the course. Well, it is a part of the demonstration in the course which will come later, right? So we will talk about OTDR not as a kind of a theory part, but there are some demonstration videos that will appear in the later part of the course. So you will see something about the OTDR. What is evanescent field effect? So if you don't know about it, it's fine. But to give you introduction, let's say you have a fiber core and a cladding. Again, this is a part that will come in the later part of the course. Whenever you have light being guided in the fiber, there is a small part of energy that is available in cladding, and that's your evanescent field. That doesn't carry energy outside the cladding, but then it is available. Devdatta, the question is spectral efficiency is limited by SNR. So how can we deal with this thing? Well, you can't deal with this thing. Shannon in 1948 already said that you can't keep on increasing spectral efficiency, and that's bounded by your signal to noise ratio. So you are theoretically bounded by the spectral efficiency on the amount of data that you can transmit through any channel. Why it is bounded by SNR? I mean, one has to look at the derivation of Shannon's theorem, but that's a beautiful information theory based derivation one can do. But the bottom line is that the amount of data that you can transfer is decided by the signal to noise ratio. So what you can do is to get up to the Shannon's capacity limit. And at the moment, we are not even reaching very close to Shannon's capacity. We are way away from Shannon's capacity. So by doing coding, by doing forward error correction, etc., we can work with low signal to noise ratio conditions also, but that is still bounded by Shannon's capacity. How good future is fiber optic communication? I mean, I don't know how to answer this question, Chaudhary. Future of fiber optic communication. You're talking about the future of a technology which is driving this very connection that you and me are having right now through this YouTube link, right? Especially in the era of pandemic, you're all dependent on communication technology to talk to each other, to entertain yourself, to educate yourself, and you're using this technology more and more and more. And as I told you in the week 1 lectures, the backbone for all of this is your optical fiber communication. So if there is a future for any technology, it is the fiber optic communication technology that is going to have a future. Yeah. Kindly explain Shannon's theorem in terms of submarine fiber optics, whatever you discussed in week. So when you talk about submarine fiber optics, I suppose you mean to say the submarine communication that happens. You see, Shannon's theorem is not dependent on the channel that you're using. Whether you're using a free space channel, fiber channel, water channel, air channel, vacuum channel, Shannon's theorem holds good. So the Shannon's theorem is the same whether you're talking about submarine communication or whether you're talking about free space communication or wireless communication or fiber optic communication. So the explanation is the same. So BTS means tower, BTS means base transceiver system. Oh yeah, so this is regarding the previous question on microwave versus fiber for tower to baseband unit. So many systems today are deploying optical fibers to connect between their antenna towers to their base stations. Even in the centralized RAN systems, which is the CRAN, which is the latest standards that are coming up, there also the plan is to use optical fiber communication between the baseband units, the centralized baseband units, to the remote radio heads. So they are using wherever possible optical fiber communication. Guru has a question. What is the percentage loss of polarization mode dispersion in single mode fiber? Again, this is a topic that we will discuss later in the course. So please be patient, stay with the course. We will be talking about this in the later part of the course. What is OTDR? OTDR is an optical time domain reflectometer, which is a device commonly used by telecom operators to find out where if there is a fiber cut and where the cut is. So whenever you deploy optical fiber underground and because of some reason if there is a fiber cut, typically the fiber cut happens when some other utility service is digging and they cut the fiber. The end result is that you do not have the connection. But now how do you find out whether there is a cut in the fiber or not? So what you do is at the transmitter end, you send a pulse. It works like a radar. So you send a pulse. Wherever there is a cut, there is a discontinuity, the pulse reflects. So you keep watching out for these reflections, and depending on when you get the reflection with respect to when you send the pulse, you can find out where the location of the cut is, and depending on the nature of pulse that is coming back, you can find out what is the nature of the break, or if there is a bend, if there is some other damage. So OTDR, time domain reflectometer, is a device which will help you to analyze that. And as I said, that will be shown as a demonstration video later during the course. The important announcement I have for all those who are staying with the course is that, by this December, you would have finished the course. And if permissions, we get enough permissions, the plan originally was to have associated laboratory course along with this course, where the top few students would be invited. When I say top scoring students from this course would be invited to IIT Madras, and you would get to actually experience a laboratory course with in our labs. So that was a plan, but of course with the pandemic things might get a little bit delayed, but that is still the plan. So you will get to use these transmission systems. You would get to actually basically work with OTDRs, splicing, and so on, right? So please stay with the course, and depending on your interest, we will give you the opportunity to come to the campus and actually do some of these laboratory courses. There's a question by Sarveshwar Rao. What is the present data rate and its bandwidth, and is the bandwidth infinite? No, bandwidth is not infinite. So as I said, in the last video I have said, the bandwidth is finally, the usable bandwidth is decided by how fast can you modulate. So it depends on the transmitter, it depends on the receiver, okay? Even though we say infinite bandwidth, it is infinite. Infinity is also always a quantity which is a very relative quantity. It is with respect to what? So it's infinite bandwidth with respect to wireless communication, right? Why is the other question was, what is the present data rate? So this again I have mentioned, the commonly deployed systems, long distance systems today have a data rate of 100 gigabits per second, right? And the standards are emerging for 400 gigabits per second. In fact, some of the deployments are also happening at 400 gigabits per second. And the next standard that is expected is that of 1 terabit per second. Okay. The next question is from Bhargav. Why is fiber cable so sensitive and not flexible? Okay, you mean to say the cable that are actually deployed on the ground, they are made intentionally that way because they are basically getting deployed in the ground. So you don't want them to break or bend depending on something moving on the road, or you're basically protecting it from the environment. You don't want water to seep in. You don't want something else being kept on top of that. Other service utilities cables could be kept on top of that. So you don't want this fiber to be crushed. Ultimately, optical fiber is made of glass, right? It's a glass which actually works, a glass of the thickness as that of our hair is what is working to transmit this huge amount of information. But you can't put the glass directly under soil, right? So you need to have this kind of protection against rodents, animals. You need to have protection against. So you have armored cables so that you don't have any creepy crawlers going inside and kind of eating up some of these plastic coverings and so on. So that is why it becomes very, very rigid by the time it is cabled. So another question from Capiro. In a transceiver, we are using a RJ cable to radiate the signal from the antenna. Is it possible that you use the fiber media, FTT media, to decrease the passive effect of RJ cable? So this is kind of related to what I answered earlier. A lot of connections, copper cable connections in antennas, whether it is in wireless communication systems or in radar systems, they are being replaced one by one with optical fiber cable, because in all those wireless communication systems and radar systems, or rather mostly in wireless communication systems, the carrier frequencies are increasing, your bandwidths are increasing. So copper cable cannot tolerate, or it cannot handle that larger bandwidth for long distances. So they are being already replaced by optical fiber cables. Rakesh Singh has a question. How do you reduce losses? So we will, again, this is a topic that we will discuss later when we talk about optical fiber. There's a fundamental limit posed by the material, the silica material itself. You cannot reduce the loss lower than that unless you think about some really special fibers like hollow core fibers, right? Some researchers are saying that, instead of a solid fiber, what if I use a hollow fiber, right? But then there is no material, so there's no loss. You can have vacuum and so on, right? But then these are all at research levels. Are the live sessions weekly? Yes, that is a plan. I plan to weekly meet at 5 o'clock, and we would like to keep it between 5 to 6, where you can ask questions. See, this discussion will become very useful only if you ask questions related to the video content that you covered during the week. You ask random kind of questions. I'll keep answering random questions, but that is not going to help you understand the course better. Okay, it'll give you a general idea, but then if you want to follow the course strictly, I would say that come prepared with your questions related to what we did during the week. Okay. Which software tool is used to check the performance of fiber optic link for research purpose? So that's a question from Ravi Patel. So Ravi, there are so many commercial software that's available in the market. I don't want to endorse for anyone because I don't use anyone, right? For all our research purpose, we write our own code, right? So because we know the function of each module, and so we write our own code. But having said that, there are several commercial softwares that are available in the market today that will help you design a optical fiber communication link, and it's not at all complicated to write your own codes to evaluate the performance of communication link. Alpesh, please guide, if possible, any good software or tool available for planning of the fiber links and the SDH, the DWDM systems. Again, as I said, the answer is the same. There are different software is available. Each one is good in their own respect. So I don't have any specific recommendation for any specific software, simply because I've always used my own codes, and we have used some of the commercial softwares like VPI or Opti system and things like that. But each one has its own set of limitations. Each one has its own set of advantages. Why do we talk about WDM instead of TDM? So TDM is definitely there in optical communication, and we will also talk about WDM, but again, it's a part coming up later part of the course. So I would again ask you to stay with the course, and please raise this question whenever we are doing that part of the course. Outdoor deployment of OFC, again, I will say that it depends on where you are deploying it. So if it's, it depends on the terrain, just like what are the factors that you would take care if you're trying to deploy an electrical cable. A similar thing you would do it for an optical cable. Bhargava, why they say that 18 to 25 dB at receive is good for bandwidth? I would say please stay with the course, and we will be talking about the link design, what is the requirement at the receiver, and so on. We will scientifically derive what is the sensitivity required for a given bandwidth and so on. So please have patience, stay with the course, and you will get to know all this later. Pooja, I missed other classes. No, this is the first, this is not a class, this is an interaction session. I repeat, please ask questions related to the content covered during that week if this session, you want to make use of this session. Okay? If you want to really make use of this session, if you want to make use of, please complete the videos of the week before this session. Write down in your notebook what are the questions that you have about those videos that you saw during that week, and then ask. That will be much more fruitful. What is the difference between decibel and dBm when we are trying to test the fiber cable? Okay, so this is again covered in the last video. I've explained clearly what is dBm. So this is power in dB. So you take power in milliwatt, convert it into logarithmic unit, you will get power in dBm. So let's say you have 1 milliwatt of power. Logarithm of 1 is 0. So that corresponds to 0 dBm of power. If you have 10 milliwatt of power, you get 10 dBm of power. dB is a relative scale. If you're trying to compare power at the transmitter and receiver, let's say the power at the transmitter is 1 milliwatt. The power at the receiver is 100 microwatt. In case of dBm, if I convert into dBm, at the transmitter it was 1 milliwatt, so it is 0 dBm. At the receiver it is 100 microwatt, which is 0.1 milliwatt, which is minus 10 dBm. So the difference between the powers in dBm will give you the dB loss. So it is a 10 dB loss in the link. You can also do this dB as 10 log of output by input. So 10 log of 100 microwatt divided by 1 milliwatt would also give you a loss of 10 dB. I hope that is clear. Pranay, I'm not going to answer this question. I've already answered scope of fiber optic network. Any possibility that bidirectional signal collide to disrupt speeding or connection? No, there is no. Usually, bidirectional signaling is done with either two colors, two wavelengths, or with two completely different fibers. So there's no possibility of any collision. What is the content for the next class? It is already put up in the Moodle page. Please follow the Moodle page. Can we use rectangular pulse for OK instead of square pulse? What is a rectangular pulse? Square pulse, both are actually the same in the sense that you are filling the entire signal slot, right? So there's no difference. Visible spectrum 480 to 780 or 380 to 700, it depends on how you are defining this. I really don't remember whether it's 480 or 380 or 400. You can look up Wikipedia. Is it possible to make direct duplex communication with you? So a lot more questions. So there is a course forum, right, on the Moodle. So sorry, in NPTEL webpage. So please ask your questions in the course forum. That will get answered. And I encourage you to please keep asking your questions in the forum. Okay, so that is probably the end of the questions. And we are at 6:10. So are there any more questions? Can we use a sync pulse instead of square pulse in OK? Yes, you can use a sync pulse, and that exactly is Nyquist shaped pulse, right? So you can tailor the spectrum. That's possible. What type of fiber? Stay with the course. You will see what type of fiber is required for gigabit speed. If I answer all the questions related to what is coming in the course, then you won't do the course, right? So please stay with the course and stick to the videos in the course. Okay, so thank you very much for all your questions, and we will meet next week again. Yeah, can we close? Yeah, bye. Yeah, thank you very much.